work of our binary search, and at the same time, we'll look at the efficiency analysis. All right. Okay. Now, let us understand binary search. When we go through the whole binary search at the same time, we do efficiency analysis. Okay, yeah. We want to count the number of comparisons for the worst case. Here. Worst case, not the best case, because best case is trivial. Your best case is V equals the median. That's your best case, right? So V equals the median. Then one comparison, you get a solution. That's trivial, so we don't consider this case. All right. The worst case, then we need to spend a lot of time to consider the worst case. Yeah. All right. Let's draw this diagram. We assume this line segment represents an ordered array, ascending order, right? The first time this is our V, our key, compare it with the median element. All right. After the first comparison, we eliminate one of the two subarrays, right? Yeah. Either the first subarray or second subarray. We can drop it from our consideration. Okay. All right. After we drop the first subarray, we have data that is approximately 1/2 of the original data size. Yeah. Half of the line segment. Yeah. The second time, we do another comparison with the median of the current subarray. Yeah. The result, still, we drop 1/2 of it. Okay. And we do this again and again until we get to the last step. We have to stop somewhere, right? But where to stop, at this point, we do not have a good idea. Yeah. After how many number of comparisons we have to stop? At this point, we couldn't figure out. Yeah. But later, we need to figure this number out. Okay, yeah, because that is important. This number is important. Yeah. Let us draw this chart to understand the data reduction procedure. Yeah, all right. Number of ops, number of comparisons. The first comparison that cut the data size 1/2 of the original. Okay, second comparison, then the remaining data size 1/4 of the original, and so on. After case comparisons, then the data size to be considered, it becomes m over 2 to the kth power expression. Yeah. So you can see the data size is reduced quickly. Right? Every time divided by 2, cut it in 1/2. Yeah. So this reduction is pretty fast. Okay. All right. Then now we like to figure out this K and see for what K we reach the end point, the last comparison. The end. Yeah, that number is important. We need to figure out. Okay, so the question: at what time should we stop splitting? Okay. Can you find a condition? You know, we can call it stopping criteria. Stopping criteria. Okay, yeah, you have to stop. It does not make sense for further splitting. We need to find that condition. All right, so let's look at this. After the last comparison, let's look at the data size we have. Yeah. Based on our, the chart here, we have some suitable data size we can use for our analysis here. Think about if the data size less than 1, should we do further splitting? Yeah, because look at this fraction. It is a number, right? There is a possibility this expression less than 1, right? When k is sufficiently large. If it is less than 1, that means it can only cover, so you have an interval. The size is this length. This length, that's the size. Length of this small line segment, that's the size. If the size, the length, less than 1, it can only cover one integer, right? Can cover one data item, not two. If you have two data items, the difference between two data items, that's 1. All right? But your interval is less than 1, so you can only cover one element. If you have only one element, there is no reason you want to do further splitting. So you have to stop. So here, this condition gives us the stopping criterion. You have to stop if you detect the data size is strictly less than 1. Yeah, strictly less than, not equal to. If equal to 1, you have a chance to here. This is equal to 1. You have chance to cover two elements, right? Two elements. So you need to do one more splitting. Yeah, but here strictly less than 1. No reason to do another splitting. So that is the stopping criterion. All right. So with that, because this is our size expression, the size, the current size, this is current size. The current size is strictly less than 1. The second one is the previous size. Previous size is greater or equal to 1. Okay. If you find this kind of k satisfying these two inequalities, that k corresponds to your last round comparison. That's the accurate analysis we need here. All right, yep. Since we have this inequality here, we can write an equivalent. Yeah, this one we just remove the common denominator, so we get a more friendly expression. Same equivalent condition, but this version more friendly, right? Yeah. So then after that, we solve this inequality, or these two inequalities, we can get new expression. This time we try to, get our k out, because k is our, our goal. K expression is our goal. All right. So, yeah, in that way we have to use log base 2 expression for m. Yeah. All right. So then next, here for the worst case k, it is satisfy this inequality. Okay. Yeah. But inequality, when we use inequality, that means still there is some room for k, right? The k could be in a range. So that expression still we feel not quite accurate or precise. So we want to make that inequality to equality. If we use equality expression for k, then that is very precise, right? Yeah. So that is not a range expression. We know inequality, that is a range expression, right? In that range, you have some freedom to move around, right? But now, if we have an equality, then that is accurate, okay? All right, let us derive the worst case formula. All right, we start with the equivalent expression. Yeah, here, another way to write, the previous inequality, we can write in this way, okay? Yeah. Now, because this time we put K in the center, and the K has a lower bound and upper bound. Yeah, lower bound and upper bound, okay? The difference between the lower bound and upper bound, look at the difference, is 1, okay? The difference is 1. That means we can find an interval with the length 1 to cover this K integer, all right? Yeah. Can we find integer expression for K? Yeah, because that interval can only cover 1 integer, because this is an inequality, okay? Yeah. The left side inequality is strictly less, not equal. So that means this interval can only cover 1 integer, okay? Yeah, all right. So now we can write in this way, yeah, yeah. Because look, why we switch back to the exponential expression, the reason is log base 2 of n, it's a non-integer, right? Non-integer. All right. And look at the expression here, we have integer expression. Yeah. Everywhere we have integer expressions. Integer expressions, we can do better, right? Yeah. When we consider the errors, we can do better for integer expressions. For non-integer expressions, the fractional part, it is not easy to control that fractional part. So that's the reason we switch back to the, exponential representation. Yeah. All right. Then look at that. All right. So here. All right. And yeah, look at the right-hand side inequality. N strictly less than 2 to the k. Can we write n plus 1 less than or equal to 2 to the k? Yeah. N is an integer. 2 to the k also an integer. One integer is strictly than another integer. Then we increase the smaller one by 1. Can we say this n plus 1 is less than or equal to 2 to the k? Look at that logic. Look at this logic, okay? We know n is strictly less than 2 to the k. Then we can say n plus 1 is less than or equal to 2 to the k. Yeah, there is a possibility they are equal, but there is some bigger chance n plus 1 could be less than, strictly less than 2 to the k, right? Yeah, that's the right-hand side. How about the left-hand side? Yeah, all right. So the right-hand side, with this new expression, we take natural log, we can get this. Look at that, okay? Natural log, we can get that, okay? K greater or equal to log base 2 of n plus 1, all right. Then this side, look at that, okay? Yeah, because look at this inequality, okay? Yeah, we take natural log, not natural log, log base 2, k minus 1 less than or equal to log base 2 of n. At 1 both sides, k less than or equal to log 1 plus, okay? Yeah, 1 plus log base 2 of n. That is this one, okay? Yeah. So we have a new inequality expression. K is between these two log base 2 expressions. All right. Now, the last step. How do we get integer expression? Our goal, we want to find an integer expression. How to get that? Okay. Conclusion, two formulas. Two formulas we have for the integer expression. The first one, yeah, K max, yeah, max, the maximum number of comparisons we need for binary search. K max is the ceiling function of the lower bound. Yeah, this is the lower bound. But we know K greater or equal to that log base 2 parenthesis n plus 1. So we should take ceiling function. That is the first formula. Okay, yeah. All right. Can we use the upper bound function? Upper bound function greater or equal to K. So we should use the floor function here. All right. So our second formula, K max, there is another representation. K max equals 1 plus the floor function of log base 2 of n. Yeah. These two formulas looks different, but they have the same value. Same value. Okay? Yeah. Because we know the integer between upper bound, lower bound, there is only one integer between, only one integer, K max, between upper bound, lower bound. Now we have two different expressions for this unique integer covered by that interval, right? So they should be the same. All right. Based on our analysis, these two expressions should be the same, although it may not be obvious, right? When you look at these two expressions, it's not that obvious. They must be the same. Yeah. And we can use mathematical induction to show they are the same. Mathematical. So we have this formula. Yeah. These two expressions are the same. Yeah. And this equality can be proved by mathematical induction. Okay? Yeah. Yeah. All right. Yeah. We have less than 10 minutes. Yeah. Yeah. Actually, in my notes, I have the mathematical induction part. Yeah. Let me see, because still we need to do a lot of work. Yeah. 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 The best case, we know one comparison. The worst case, we have this expression, 1 plus, yeah. Yeah, you can use second expression, the first expression equivalent, okay? Yeah, but after this class, you need to be able to identify that these two expressions are the same, okay? You need to know this, okay? All right, I may skip the mathematical induction part, yeah, because it takes too much time, yeah, at least half an hour. Yeah, yeah. At least I need to spend half an hour to, go through the details of that mathematical induction. Yeah. But here I like to talk about the average case. For binary search, how to calculate the average case. Can we say the best case plus worst case divided by 2? The answer is no. The answer is no for binary search. All right. The answer is no. We can, if we do this way, conceptually, it's not correct. Yeah. You may argue this expression is very close to average case. Even you make that argument, it is wrong. Okay. Yeah. Actually, the average case is slightly smaller. Slightly smaller than the worst case. The difference is less than 1. The difference is less than 1. Slightly smaller than the worst case. All right? Yep. All right. All right. But the question, how to calculate the average case? Yeah. Yeah, let me see.